Good. So then the topic is numerical arrays, cell arrays, and structures. And the main thing about these concepts is that they are data containers. Yeah. So in programming, we often deal with numerical data. So you have numbers, for example, because you acquired some experimental data. And then an important thing in analyzing data and doing science essentially on data is to organize the data in a way that you know what's going on. And numerical arrays, cell arrays, and structures give you some basic means to organize numerical data. By now, there are also additional ways to organize data in MATLAB. For example, tables. They didn't have to do that. They didn't have that for a long time. So I'm not talking about it. If you're familiar with R, they had tables for longer. So MATLAB adapted a little bit to that. So tables allow you to store a little bit more metadata with your data. So not only the numbers, but also description of the numbers, like what is in the columns and the rows of the data that you save. But yeah, that's something, once you're familiar with the basic things, then you can also look into tables. Yeah, so the first thing then to talk about are numerical arrays. And if you watched my great video on MATLAB matrices, where I almost fell asleep when doing that because nobody was there that I was talking to, so let's see how that works for the stats stuff. Then you already have seen numerical arrays, but these are two different viewpoints on the same entities in MATLAB. So essentially, numerical arrays, at least two-dimensional numerical arrays and matrices are two-dimensional entities with data in them. So let's first make this concrete so that we know what we're talking about. So I'm making up now a numerical array / a matrix with some numbers. Don't have to stick to what we have in the script. So I'm making up this as we speak, or not speak actually, oops. And let's make a fourth row. So now I specified using the syntax that we discussed very previously in the matrix section to come up with a matrix or a numerical array. So this numerical array is called D. It's of size 4 × 3, so it has 4 rows and 3 columns. It stores double precision numbers, and these are the numbers. So what is my thing with the matrix versus numerical array? Now, if you're thinking from linear algebra, this would be a matrix, and you could now add another matrix to it, or invert this matrix, or multiply it with a matrix, depending on its size. From the perspective of the numerical array, these kind of operations that you can do it are not that interesting. What is more interesting from the perspective of a numerical array is that you have saved some data in this table format in rows and columns. So for example, if you're thinking about a cognitive neuroscience experiment, the data here could be reaction times in milliseconds, and the columns could be conditions, so condition 1, condition 2, condition 3. So for example, responding to different kind of stimuli and how long it takes you to give a response on what stimulus that is. And the rows could be participants. Yeah, so you have 4 participants, and each of them took part in an experiment, and you have these, let's say, median reaction times across the 3 conditions. And now what you want to do with this data is not necessarily do matrix multiplication with it, because that's something that you do when you do linear algebra. If you look at it from a perspective of a numerical array, then you rather want to, for example, extract the data that belongs to a certain participant, or you want to average the data and compute summary statistics on this data, and you don't care about linear algebra. Yeah, so these are these 2 perspectives. And this is also important if you, for example, start to deal with multidimensional or more than 2-dimensional arrays, maybe 3-dimensional arrays, where you include pages. So you have a 3rd dimension, which maybe I can show you that briefly. So let's make up another array quickly with the rand command. So if we have this, then we have, maybe let's take this times 1000, so that's a little bit nicer, and maybe let's make it look even nicer. So if you have another array of the same size, so you have now this D and E, what you can do is stack these arrays as pages in a 3-dimensional array. So now F is a 4 times 3 times 2-dimensional array. So you can view that as a, if you want, as a not a cube, but like this, something like this, which has some 3D extension. And on the first page you have what was there for D, and on the second page you have what was there for E. The reason I'm bringing this up with more than 2 dimensions is that these things don't exist in matrix algebra. Yeah? So there are no 3-dimensional matrices in linear algebra, or 4 or 5-dimensional matrices in linear algebra. Unless you develop a mathematical theory about 3-dimensional matrices, then they are of course there. But in standard linear algebra, everything is 2-dimensional. And you can basically increase the dimensionality to 4 and 5 and so on dimensions, and then it's all about indexing. So I don't want to go down there, because that's specifically when you start out with programming, that might be a little bit confusing. So we return to our 2D example, and now view that as data array, where we have some data and we can work with that. Okay, so the basic thing that you can do if you have a data array is that you, for example, can extract data, and this you do using subscripts, which you write into normal brackets. So, for example, if you want to extract the element in the 2nd row in the 3rd column, you index this by the row index 2 and the column index 3, and then you get what you saved there. So let's go up here again. And you can, like for matrices, as I discussed them previously, you can also extract full rows and full columns. So, for example, if these are conditions in the columns and rows, conditions in the columns and participants in the rows, if you want the data from, let's say, the first participant, then you want the first row. So you can extract this by saying, I want the first row, and I want, and this is what you specify with the colon operator, I want all data points, so across all columns. and that's then what you get. Likewise, you could say I want the data from one condition, so I want all rows, for example, in the third condition, and this is the syntax to get this. Then what you can also do as a basic manipulation is that you can say, okay, somehow the second participant, something was funky there, so I want to remove the data from the second participant from my data set. And to do that, to delete full rows and 4 columns, you can use the following. So you specify which row or column you want to delete. Now I want to delete the second column, and then you set this to the empty array, and this then removes the entire second row. What you cannot do is remove individual elements, because such a numerical array is always 2 times 3 dimensional, so you cannot just delete one number and then have in the first row only 2 columns and in the remaining row 3 columns. That doesn't work. But what you can do, if you, for example, want to exclude some data, let's get back to our full array here. If you want to exclude some data because you think, for example, in terms of reaction times, this was an outlier here, what you can do is set certain elements to, for example, nonce. So this is the first column, second row, so it's second row, first column. So you can, instead of extracting, you can also manipulate the data in there by indexing it and then setting this, for example, to none. And then you have here the entry not a number, which basically signals that this is not some data that you want to process any further. Yeah, you can, so MATLAB is quite versatile in what it allows to do. You can do things that seem maybe not that sensible. So because MATLAB has something called scalar expansion. So if you specify, for example, that you now for some reason want to set all the data in the third column to none, you can do this by specifying that you want all rows with the colon operator, the third column, and setting this to none. So, none. So if you think about it, this statement here doesn't really make sense, because on the left-hand side you say you want all rows and the third column. So this is actually a 4 times 1 dimensional array or vector. And on the right-hand side you're saying none, which is a scalar variable. So you're basically setting a 4 times 1 dimensional vector to a scalar. That doesn't make sense, but what MATLAB does is that it uses what is called scalar expansion. So if you here specify a scalar, you can also not only do this with nonce, of course, but also, for example, with 1. It automatically assigns this scalar to all the values that you have there. And that's a little bit weird because, for example, if you don't do this with a scalar, but with another vector, and this vector, so now this would be the 3 times 1 dimensional vector 1, 2, 3, and this vector is not of the right size, then you get an error, because of course 1, 2, 3 doesn't fit into the slot of 4 rows and 1 column. But if you do it with a single scalar, it works. So it doesn't make much sense, but this is scalar expansion in MATLAB. Okay. So these are basic manipulation to extract data. And then there are, of course, also some basic commands to create arrays and matrices. So I talked about that in the video. So you can, about matrices, so you can come up with arrays, for example, using the run_n command, which gives you standard normally distributed random numbers, so with expectation parameter 0 and variance parameter 1, and you specify how many you want. So for example 2 rows and 5 columns, and then you get that, but of course it's some random data. So this can be done to create things. What is more interesting usually is to do logical indexing, because often you want to extract data from an array that fulfills a certain condition. So let's go back to this. So for example, you want to figure out which participant showed median reaction time of 516 milliseconds, 516 milliseconds. And to this end, the find command is helpful. So that's find that. This is the helpful find. So find is something that you, especially if you're doing basic data analysis, should acquaint yourself with. It allows, based on some logical statement, to obtain indices. And there are two kinds of indices in MATLAB, namely the subscript indices, which give you the row and column and page, and if you go into higher dimensions, all the subscripts, and linear indices. I generally recommend to stay away from linear indices because they depend on the size of your array. So linear indices are these indices that just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But one also often is not sure whether actually the linear indices run over rows or columns and so on. So I, in general, I recommend to stay away from linear indices and always use subscripts. So if you call find with 2 output arguments, namely row index and column index for a 2-dimensional array, and specify some conditions, for example, find these indices where d equals 516, then find goes over the array d, checks where this is actually the case, and returns your indices. So it says it's in the second row and the first column, which is here, and you have now the indices. Yeah? And that's good. Yeah. You can also use different logical statements. So, for example, find everything where d is larger than 200. So then you get the row and column indices. And that one always has to check a little bit how this is returned. So you can see that for the rows in the first row, in the first column, in the second row, in the first column, in the third row, in the first column, this is all larger than 200. So here you get the row indices and you get the corresponding column indices in this other output argument. And so then you have to make sure that you match them, but you'll get all the row and column indices for these for the entries of the array that fulfill this condition. In general, so using this logical indexing in MATLAB requires some experience. So in general, if you extract data, you should always, and especially use these logical indices, you should always check your results. So even after 10 years of MATLAB programming, actually, when I started MATLAB programming, I always thought, I understood what's going on, so just leave it, just write the code, and then hopefully it runs. But now I really recommend that you put in many checks to make sure that it actually, if you use logical indexing, that it returns what you want. There is much more also to logical indexing. So the way I think about logical indexing these days is more that these kind of statements, they instead of using find, they return logical arrays. What I mean by that is if we think this is D, and now we specify a logical array D larger than 200, then what this returns is a logical array of the same size as D, where each entry signifies whether the entry of D at that location is fulfilling this logical condition or not. As you can see, it has ones where it's larger than 200, and it has zeros where it's not larger than 200. So here, of course, you don't have the column or row indices, but you can use these kind of logical arrays quite nicely to extract data. So if you want to extract all the data that is larger than 200 in your array D, you can index D using this logical array. And then you get the data, although you get it here then as a column vector, where of course the information of where this data is coming from is lost, but at least you get all the values in the array that fulfill this condition. So this can also of course be done in one step. So here, so this is also a valid MATLAB count. So here, if you want all the data points in D that are larger than 200, you can write something like this. So D at the location where D is larger than 200, and this returns this logical array that I just showed you, and then this logical array is used to index D and returns the data in a column vector. So that's, I use actually this logical indexing much more than this find command these days. Questions right now? Good. So maybe more interesting or at least more straightforward than indexing and extracting data and so on is computing on these data, because this is then really where things that you are familiar with come in. So for example, if these are participants and these are conditions, a very natural thing that you want to do is to compute the mean over participants. And for this, there are basic functions in MATLAB. So, for example, if you want to compute the, call it the mean of D over participants, then you use the mean command, and then with these commands that you can use to compute basic summary statistics, usually comes the need for specification along which dimension you want to compute that. So if you don't specify anything, it will do it over rows. So now you have the mean for each condition. It's better practice, however, to specify explicitly along which dimension you want to compute the mean. So if you look into the help of mean, mean x takes the mean along the dimension dim of x. So the same thing that I just showed you could be achieved by saying, okay, I want to compute the mean over rows. So I say along the first dimension, then you get this. But you can also, of course, compute the mean now over conditions, so that you get a single number for each participant. This would be along the second dimension. and give you the corresponding outcome. You see also that this comes out as a row because you took the mean over rows, and this comes out as a column vector because you took the mean over columns. There is another basic descriptive that you of course always want is the standard deviation, and there MATLAB pulls a nice trick on you because one would think that, for example, if you maybe before I show you standard deviation, I show you sum, and then I'll tell you about this little trick that MATLAB does to annoy you. So if you have D and you want to sum, for example, over rows, so then you can just write sum D1, so then you get the sum of these. You can sum over columns, then you get the sum over columns. Same, by the way, maybe we go on with this. You can get the minimum arguments over rows using the min command. Oops, no. No, sorry. That does something else. See, this is actually the same thing that happens with standard deviation. The second argument that you put into these basic functions to compute statistics is not always the dimension, and this is just what I realized here again. So if you think about again how we computed the mean over rows, we put in a second argument 1, so we get the mean over rows. Now, if you use the command standard deviation, the second argument that you put into the std command actually specifies what kind of standard deviation it's computing. So essentially whether it's computing the biased or unbiased way. And only the third argument specifies along which dimension. So this computes the standard deviation along rows, and this computes the standard deviation along columns, and the element that I left free here, that specifies how the what you have in the denominator of the standard deviation, the formula. So either normalizing by n or by n minus 1. And that's something, so one needs to be aware of, because if you think that everything is logical in programming, and if you have this function that uses as the second argument along which dimension you compute this, like for mean or for sum, and then you have other functions that in principle do the same thing but compute something different, then it's not necessarily the case that the different arguments also refer to the same thing, which is a little bit mean and which allows things to go wrong. So always check again when you're programming what's actually going on. So let's look at this thing that I now had the problem with, namely min. Min is the same thing. If you want the minimum over columns or rows, you have to specify this as the third argument. So let's look at D again, and let's say we want the minimum of D over rows. Then we do D, second argument does something different, 1. So we get here 156, we get here 178, and we get here 176. And now we want the min over columns. Then we need the second dimension here. Then we get our 343, 178, 167, and 156. if we want the minimum of the entire thing, which is something that one often wants, then one can do the following. One can do minimum of D, which first does the min over rows, and then use min again on this row vector, which then just returns the minimum of this row vector. So if you want in a two-dimensional array, if you want the overall minimum or maximum, you can use this nested approach to using min. Again, there are different ways to use these basic functions. One way one can also use min is with multiple output arguments that return both the minimum value and the indices. However, here in a linear sense. So let's see what we get there. If we do min d index, then we get, first of all, we get the min over rows. So we get our 156 and so on, and we get the linear index. So we don't get the subscript index, but the linear index. Yeah. So again, this is more to tell you, don't use your intuition from find or from any function that you know on another function. It might be completely different. Yeah. Although the basic ideas are the same. Good. Yeah, I think I want to stop or I want to end with the exploration of numerical arrays here and go to cell arrays and structures. So are there questions right now?
How do you, how do you get back to the original D value? Because when I took out the second round,
the only way to get back to that's actually a good point. So this was our D, and then we took out the second row like this, and then we're back at this. The only way to get back to get D again in the form as it was previously was to redefine it. So we defined it originally as this, and only if you redefine it, then you get back to it.
Okay.
Yeah? Anything else? No. Good. So these are numerical arrays, and numerical arrays in this two-dimensional scenario contain numerical data. So they are allowed to have data that is of double or of single nature. But what is not working is to store strings in them. So for example, this does not work. So if I want to put in a string, namely the character A, into the first row in the second column, MATLAB does crazy shit, but it shouldn't do anything. So again, what it does is that it converts this character into its ASCII code, which must be 97, and puts this into D. But obviously, it hasn't put in the letter A there, and it's also actually it's not good that MATLAB does this. Because it should give an error and not do something and not issue an error. But as you can see, you cannot put a string in there. And you can also not, for example, in one of the locations here, 1, have a scalar, and somewhere else, for example, in 3, 2, have a vector. So if you want containers that are more versatile, so that you can put in different things to them. To do that, actually cell arrays come into play. And in my script, I figured that there are some of the brackets missing, so it was a little bit unclear what it says, what it means in the script, because what is missing there are the curly brackets. The essential thing about cell arrays are curly brackets. So if you come up with one way to start working with the cell arrays is to specify something like this. So you have A and you index A with curly brackets. So this will tell MATLAB that it should create a cell array with here one cell, and into this cell put now a scalar. So now A is a cell array, as you can see. Oops. So A is a cell, is of type cell, and at this point, has only one entry. But now if you specify a second entry, for example, a second row, and you put in a scalar, not a scalar, string, sorry, then A can hold both numerical data and character data in here, and can also hold different size data. So for example, if you into the third row, oops, sorry, that's not where I wanted. Let's build this up again. So I don't want to show this. So now back. So here A now has in the first entry it has a scalar, in the second entry it has a character, and in the third entry, so in the third row in the first column, it has a vector 1 times 3 row vector. Yeah. So actually this data container can hold all types of data, and hence is quite useful. It comes with these curly brackets, and there are two ways of indexing this. So if you want the content of a cell, then you need the curly brackets. So if you, for example, want the vector, oops, I'm struggling with my indices today. So here you get the vector. If you want the cell itself, you use the normal brackets. And I just can't do indices today. So you have to view this. So essentially, the components of A are cells, and these cells have content. And to get the cell, so basically just the component of A, you use the normal brackets. But then what you get back is a cell, a single cell with some content. Yeah? If you want the content of the cell, you use curly brackets, and then you get what is in the given cell. Now, that takes a little bit of getting used to, because often you will want to use, once you're familiar with the numerical arrays, you want to use this and hope that you get the content, but then you don't get the content, but just the single cell that makes up A in this location.
So the first B is an array and the second B is a cell.
Yeah, and one can also check that. So maybe I give the first. So that's one can also, of course, always check what's this with the class command. So this tells you that this is of type double, so it's something numeric. And if you extract the cell itself, I mean, it says it there, but you can also check that, then you see that it's cell. Well, yeah, what you saw previously briefly is that, like for numerical arrays, MATLAB does its thing when you specify something. So, for example, if you specify now that you have this 3x1 cell array, you specify something for the fourth row, the fifth column, and you put in, let's say, a matrix there, because that's of course something that you can also do. Then MATLAB automatically expands the array. This is what happened previously, and fills in empty cells everywhere where you haven't specified anything yet, and the thing that you are interested in the look at the location. Yeah, so it from having this cell array, because you specify at row 4, column 5, you want a matrix. It does that, and at the same time puts empty cells everywhere else. Yeah? So it does its thing.
Can we add another cell in one of the cells? Okay.
Yeah, you can do nested cell arrays. So, for example, if you specify, let's specify something like this. And B to 1. So we have now a cell array, and we can put this cell array into one cell. So let's, for example, put it in A here in the first row in the fifth column. That would mean first row, fifth column, and we assign B. Then we have there a cell array in there. Yeah. And of course, you can also put cells back into this one, and you can, yeah. Yeah.
If you use normal brackets, A normal brackets 1, 5, and something, could it do anything?
So if you change this,
yeah.
Let's see what happens. So how do I interpret this? So that doesn't work because we use cell addressing. My interpretation of why this doesn't work would be that these are two cells, and this is one cell, and you these are two cells because it's a cell array, and these are two. This is just a single cell location. So let's see if we redefine B as a B as a single cell. How that works. Oops. Yeah, that's also something that happens. So if you have B specified, so B was this, and then you try to address it as a cell array, that doesn't work, and this is the error I just got. So let's come up with this. So now C is a one cell, and we want to put in 1, 5 of A. Let's look at A again. And C is this, and maybe let's put it at 1, 4. Yeah, so that works. So because this here is a cell of this array, And of course, we can replace this cell, which was the empty cell, with a cell that contains something. But we cannot replace this one cell with multiple cells, what we tried to do before. Yeah? So let's not go further into this, because you will use cells. One reason to use cells is if one deals with the strings. So for example, if you want to load a number of files and you have all of them specified as strings, because that's the location in terms of the path and the file name, then you might want to use a cell array. And because you cannot use this in numerical arrays, and then you can start to get used to becoming familiar operating with cells. So they are quite versatile, but in a way also sometimes a little bit confusing, because you always have to think differentiate between the content of a cell and the cell itself. So one data type that I prefer personally are structures. Before we talk about structures, any other questions about cells? No, good. So structures, so that's then the last bit for this first hour, or more than 1 hour. Structures are like cell arrays in the sense that they can hold whatever data you want them to hold, but they come with a little bit more meaning, in the sense that you can give names to the fields of the structure. So, for example, that's the example in the script, obviously. If you want to specify a circle, then that you might want to plot or so, then the circle is, for example, defined by its radius, where its center is in 2D, how you want to plot it, and what color you want to plot it. So what line you want to plot it, and what color you want to plot it. Now, to come up with a structure like that, what you use is this dot notation. So you say circle dot radius, and you assign a value. So this tells MATLAB it should create a structure, and this structure has a field called radius, and this field radius contains the value 3. Like for cell arrays, you can, in different fields of the structure, put in different kinds of things. So here in the first, or not in the first field, but in the field radius, we had a scalar. Now, for example, if we want to specify the center of a radius in 2D, we can put in a vector, and then we have our circle with radius 3, center 1, 2. And then, for example, if we want to include how to plot this and specify this in terms of a in terms of a string, we can use this also. And you can, of course, also put, if you want, for some reason, put in a cell array, which you can, by the way, also specify directly in curly brackets. You can also put cell arrays, and you can even put structures into structures, like for cell arrays. So, for example, if you're thinking you want to build a structure which has circles but also rectangulars and whatnot, you can you can specify a new structure that, as a field, circle contains a structure circle. Now, the nice thing, of course, about this is that you have explicit names, so you don't index the contents by linear or subscript indices, where you always have to think which column, which row am I in, but you index it by explicit short descriptions. So for example, if we are going back to our circle, you now want to get the center of the circle. You could say circle center, and then you get that. So you don't have to remember any row or column indices. That's nice on the one hand. On the other hand, of course, sometimes if you are using loops or whatever, then this is of course much more demanding, and you actually it's nice to use indices. So that always depends on the applications. But if you have kind of data objects where you want to in one variable collect a lot of different data, then this is helpful. What I'm using structures also a lot for is if I want to pass in multiple arguments to functions. We will see that a little bit later about functions. You can in principle specify 100 inputs to a function, but this then your code looks very long and so on. So it helps to collect these input arguments in an input structure, and then you just put the structure into a function, and you just have one input argument. But then you need to extract, of course, again. So structures are helpful, and you will see structures once you start, for example, using SPM, because the SPM MUD that is always created when you do some brain imaging analysis in fMRI data is actually a structure and has different fields. And if you go a little bit more into programming and then start object-oriented programming, structures are essentially the same thing as objects, only that they don't have functionality. But once you're familiar with object-oriented programming, structures are kind of special objects because they have functionality. There was a question.
So what do you mean by functionality, that you can add function to the structure? My original question was that if there are substructures where you have like the same features as the structure plus additional features, would you have an object-oriented programming with the airborne?
With structures, no. Yeah, no. I mean, it's different. So structures are more like a data container, and you can. They don't have functions, but the object-oriented programming in MATLAB has many similarities with structures. For example, this dot notation and so on. But it's still a little bit different. So the structures are data containers. Simple as that. And you will, if you're using SPM for data analysis, you will come across structures. Okay. Any other questions? Good, then I think that's a good time for a break. So let's stop here and then next start with control flow.